part 2 of lesson 10. And it starts off with this very important relationship, and that is that for electric fields, similar to gravitational fields, the electric field around a source charge will be different at different locations around the charge. So the further you get away from it, the weaker the field is. And not surprisingly, it follows exactly the same law as did our gravitational fields, in that the distance is inversely proportional to the force. Sorry, I should say the distance squared is inversely proportional to the force. Okay, so just keep this in mind. We're going to go into another couple of examples that are a nice review of the first part of the lesson, and then we're going to discuss why what I just said is important. So we have examples 5, 6, and 7, which we're going to go through quickly, because then they're not the kind of questions that are going to be asked as much, and I'll discuss that. I'll discuss why as we go through this lesson. So in example 5, we have a force of 2.1 newtons exerted on a 9.2 times 10 to the negative 4 test charge if it's placed in an electric field created by a 7.5 Coulomb source charge. If it's pushing west, determine the electric field at that point. So we're just getting some exercise using this formula here and reminding ourselves that the Q in this formula here is the test charge, right? So in this case, what's it going to be? It's going to be the 9.2 times 10 to the negative 4. We're going to divide those, and we're going to get 2.3 times 10 to the negative 3 newtons per Coulomb. And what is the direction of that field? It is going to be west. It says that if the force is pushing it west, determine the electric field at that point. If a positive test charge of 3.7 times 10 to the negative 6 coulombs is put in the same place in the electric field as the original test charge, determine the force that will be exerted on it. So we're going to play, this time we're solving for the force, the electrostatic force, and we manipulate that formula. And now that we've got the field strength, the electric field strength times 10 to the 3, all we need to do is multiply it by the test charge and get the answer, which turns out to be 8.4 times 10 to the negative 3, and that is also going to be west because it's a positive test charge put in the same place as the original test charge, and so on. And then example number 7, you now place a negative 4.81 times 10 to the negative 2 charge at that spot in the electric field. Determine the force on this charge. So it's the same as the previous question, except for we're placing it in the same electric field, except for now the charge is negative. And once again, I will not put a negative in there, but when I get my answer, which turns out to be 1.1 times 10 to the, I don't have the answer to that actually, so where's my calculator? There it is. I'm going to have to do this. 2.3 E3 times 1.1 times 10 to the 2. 1.1 times 10 to the 2. Because it is now negative, then what's the force acting on this charge? It's obviously going to be the opposite direction. It's going to be east. Okay, now let's move on to the heavier and more important stuff. And this is this whole concept here. We're going to take, actually, what we're going to do first, we're going to do this down below. First, we're going to review what we did for gravitational forces. In physics 20, we took two formulas, Fg equals mg, and our other formula for Fg, which is the gravitational force between two masses. So the first one is essentially gravitational field strength, or calculating your weight. this is the gravitational force between any two given masses. And since we have Fg equals this and Fg equals this and Fg equals that, then this must equal that, right? So we set them equal to one another. Let's just make that a 1. And we said M1 equals G M1 M2 over R squared. And remember that this M1 is really the test mass. So let's say I'm trying to figure out, or I'm using my mass as the gravitational force between me and the planet Earth, right? So this would be me, and then this would be me here, and then this would be the mass of the Earth. And so what happens when we combine those formulas is this, the test mass that you're using, so if, for example, I'm trying to find the mass of the Earth and I use myself as the test mass, cancels out, which is a great thing. And then we continued solving this formula, and we ended up with this formula here, m over r squared. And this was quite revolutionary because all of a sudden it eliminates the need for a test mass. In other words, this formula down here will calculate the gravitational field strength in this example I'm using of the Earth, and I don't need to use a test mass. I just need the mass of the Earth. It will calculate the gravitational field strength of the Earth at a given distance from the center of the Earth. All right, which obviously for this specific planet turns out to be 9.81 newtons per kilogram, or 9.81 meters per second squared. We're going to do exactly the same procedure with electrostatic forces. So we've learned two formulas. We've learned this one here. And from the previous lesson, from lesson 9, we learned this formula. The electrostatic force between any two given charges equals Q1, Q2 over R squared. And we'll call this Q1. And then in the previous examples, we manipulated that formula. And look at this. We have exactly the same situation. Fe equals this. Fe equals this. Therefore, sorry, that. Therefore, this equals that. So therefore, EQ, and we'll call that 1, equals K Q1, Q2 over R squared. It's identical, almost identical to the gravitational field strength. And what happens? Exactly the same thing happens, not surprisingly. Not surprisingly, the test charge cancels out, and we're left with this new formula, which I'm just going to write down the other one. And here's the, sorry, that should be little g, equals big G, m over r squared. There's those two formulas side by side, so you can see how similar they are. One is for the gravitational field strength, one is for the electric field strength. So now we have two formulas, one here and one here for electric field strength. The beauty of this guy right here is it does not require a test charge to measure the field. You can measure the field if you know the charge of the source right there, and you know the distance away from the source charge. All right, and that is all explained here in vivid detail in your notes. You can read over that. And then we can go on to the examples, I think. Here we go. Example number 8 says a tiny metal ball has a charge of -3 × 10⁶ coulombs. Determine the magnitude and the direction of the electric field at a point P 30 centimeters away. So here's your metal ball, tiny metal ball, and 30 centimeters away. It doesn't give a direction. So let's just say that this is 30 centimeters here. This is point P. right here, we want to determine the electric field strength at that point. How are we going to do that? Easy. Now that we've got this new great formula, there it is. K 8.99 times 10 to the 9, Q 3 times 10 to the negative 6. The distance 0.3. Don't forget to square it. Don't forget to change it into meters. Multiply all that out, and you get 3.0 times 10 to the 5 newtons per coulomb. And what is going to be the direction of the field at that point? The direction of the electric field it produces at that point. I'm actually not going to do that yet because we really haven't discussed positive. Well, let's do it anyway. The direction of the electric field at that point is going to be just based on what we know. We know that the point P is essentially a positive test charge. This is negative, so that positive test charge will go that way. So it will be 3.0 times 10 to the 5 newtons per coulomb toward the source charge or toward the metal ball, right? Because just to review, we always say that the test charge is a mathematical construction. It's infinitely small and it's positively charged. If this is negative, it will move towards it. Okay, but more on that later. And then the last part of this lesson is multiple source charge creating electric fields. This is more along the lines of a diploma question. It's a good question. We have two significant charges, both negative, and we want to find out what is the electric field strength at a point exactly halfway. So you see P a lot. P, exactly halfway. So exactly halfway would be half of 0.58, which would be, what would that be? So halfway is going to be 0.29 meters. And what we're going to do is we're going to calculate the electric field strength created by each object and then add them vectorially. So let's start with this guy here. The electric field strength created by that guy is going to be K. I'm gonna get lazy here. Instead of putting 8.99 times 10 to the negative 9, I'm just going to put K and 1.2, and the distance is 0.29 because we want the electric field strength at this point here, point P. Therefore, we use 0.29, the halfway point. We multiply all that together, and we get 1.3 times 10 to the 11 newtons per coulomb. So a pretty strong electric field. Then we're going to do the same thing for this guy right here. Now, before we do that, let's determine the direction. What is the direction for this one? This is negatively charged. Our fictitious point P is positively charged, so it's going to be, the direction is left. This point here would be drawn towards the left. Same thing for this one here. E equals K. This one's going to be 3.9. Again, note that I don't put the negative in there. Same distance because it's halfway. And for this, we get 4.2. 4.2 times 10 to the 11 newtons per coulomb. And what direction is that? That is going to be to the right. Because again, this positive test charge is going to be drawn to the right. And later we're going to learn that electric field lines always go into the negative and away from the positive. So that's another way that you're going to be looking at it when we do the next lesson. So this is to the right, and then we add those vectorially. One's left, one's right, so one's positive, one's negative, and you get your answer, which is going to be the net. So we're going to say the E net, the net electric field is going to equal, so we'll call this one negative since it's going left plus this little guy here, this is going right, and that adds up to 2.9 times 10 to the negative 11 newtons per coulomb, and the direction at that point is, since our answer is positive, and we designated right as being positive, to the right. Now I should have queried that out first. We should have taken an educated guess, and we should have said that this one here is much larger in magnitude, so obviously the field strength at point P is going to be more towards it. But we'll find that out in the next lesson. Okay. On to lesson 11, field lines.